In this problem, Dr. Gerd and I are cycling at the same power output and receiving the same amount of oxygen delivery. At rest and 360 seconds of exercise, we are both consuming the same amount of oxygen. However, Dr. Gerd is consuming more oxygen than us at 30 seconds, suggesting that he started consuming oxygen faster.
We will use a conservation of mass model to define the problem. The regulated variable that we decided to focus on is skeletal muscle O2. Inflow into the pool of muscle O2 is defined as O2 delivery to our muscle cells. As Dr. Gerd and I have the same amount of O2 delivery, it is clear that it is not a decrease in inflow that is reducing our pool of muscle O2. Outflow from the muscle O2 pool is considered consumption of O2. This occurs when O2 accepts electrons from the electron transport chain and becomes H2O. In order for O2 consumption to be high, there must be an increase in the number of electrons that are accepted by O2. In order for there to be an increase in the number of electrons present in the electron transport chain, there must be an increase in the number of NADH, as they are responsible for the provision of electrons to the electron transport chain. An increase in the provision of NADH requires an increase in the activity of the citric acid cycle. In order for the TCA cycle to be producing more NADH, it must be provided with an increased amount of acetyl-CoA. PDH is responsible for converting pyruvate into acetyl-CoA, and pyruvate is a product of glycolysis. If O2 consumption is increased, we expect that Dr. Gerd will be producing higher levels of ATP, which would improve his phosphorylation potential as he would have less accumulation of low energy molecules, ADP and AMP. If levels of AMP and ADP are low, there will be less activation of glycogen phosphorylase and PFK, and if levels of ATP are high, PFK will be inhibited even further. As these enzymes are involved in glycolysis, we would expect provision of pyruvate to be decreased as it is the product of glycolysis. If pyruvate is decreased, it is unlikely that it is responsible for the increase in acetyl-CoA. For this reason, we have come to the conclusion that the activity of PDH must be higher in Dr. Gerd in order for him to be consuming more O2 than me at 30 seconds.
Participants in the study were 6 older healthy male adults, aged 70 plus or minus 5 years, who were recreationally active but not involved in specific training.
Participants came to the lab on 6 separate occasions at the same time of day, 2 hours after a high carbohydrate and low fat meal. Day 1 consisted of an initial incremental ramp test on a cycle ergometer to determine each participant's lactate threshold and VO2 peak. This was the protocol for 4 of the 5 days. It consisted of exercise training on a cycle ergometer. 6 minutes of baseline cycling at 20 watts was performed. Next, 1 bout of moderate intensity activity was performed at 45% of the participant's VO2 peak for 6 minutes. This was called Mod 1. Another 6 minutes of baseline cycling was performed. Next, a bout of heavy intensity exercise at 80% of the participant's VO2 peak was performed for 6 minutes. Another 6 minutes of baseline cycling was performed. A second bout of moderate intensity exercise was performed at 45% of the participant's VO2 peak for another 6 minutes. This was called Mod 2.
On one of the 5 days, 6 muscle biopsies were taken from each subject. 3 biopsies were taken for each bout of moderate intensity exercise, one at baseline cycling, another at 30 seconds, and another at 360 seconds. 1 hour of recovery was taken before the bout of heavy intensity exercise on the biopsy day.
VO2 was measured using a low dead space bidirectional turbine and mass spectrometry. Muscle biopsies were used to measure the active form of PDH, creatine, PCR, ATP, lactate, pyruvate, and acetyl-CoA. ADP was calculated using the measured ATP, creatine, PCR, estimated hydrogen concentration, and the creatine kinase equilibrium constant.
The phase 2 VO2 time constant was reduced in Mod 2 compared to Mod 1, suggesting that the VO2 kinetics were faster during the transition to Mod 2 in comparison to Mod 1. In Mod 1, PDHA activity increased progressively from baseline to 30 seconds and to 360 seconds. In Mod 2, following heavy intensity exercise, PDHA activity was elevated at baseline. No significant changes in PDHA activity were experienced at 30 and 360 seconds for Mod 2. There was no significant change in muscle pyruvate during exercise or as a consequence of prior heavy intensity exercise. Muscle lactate and hydrogen were greater in Mod 2 than Mod 1 at baseline and after 30 seconds. Acetyl-CoA content remained at baseline levels throughout Mod 1 but increased at all times after heavy intensity exercise in Mod 2. PCR levels decreased from baseline to 6 minutes in both Mod 1 and Mod 2. However, the breakdown of PCR from baseline was reduced at both 30 seconds and 360 seconds in Mod 2 compared to Mod 1. Muscle ATP content was unchanged compared with baseline during both Mod 1 and Mod 2. Muscle ADP content increased at both 30 seconds and 6 minutes exercise in Mod 1. Muscle ADP content did not experience a significant increase until 6 minutes of exercise in Mod 2. The increase in muscle ADP content after 6 minutes of exercise was 60% lower in Mod 2 compared to Mod 1. We were correct in hypothesizing that pyruvate would not experience a significant change and that muscle ADP content would be lower. Although PDHA activity was elevated at baseline in Mod 2 and remained slightly higher at all times during Mod 1, there was no significant increase in PDH activity at 30 seconds in Mod 2, and therefore we are unable to confirm our hypothesis. The increase in muscle lactate further disproves our hypothesis, as increased levels of lactate suggest that PDH activity is not fast enough to convert pyruvate into acetyl-CoA.